All right, sounds like we're ready then. Okay, let's see where we are. I see people were talking about program 2 in the chat. How's that coming along? A little let's get ready to rumble. C and or get line, either way is fine. I'll just do single word names so that white space doesn't become a problem. And let's see how many people have made a submission at this point. 11 people, all right. About 12% of the class, thereabouts. Okay, last thing we talked about. Deleting from a binary search tree. How are we doing with building and deleting from a binary search tree at the moment? Is a binary search tree balanced? All right, not balanced. That means our annotations have a tendency to be in the linear side of things. And since that's not very good, if we had linear, might as well just stick with a linked list. So let's take a look at a self-balancing binary search tree. All right. AVL tree. These are initials for the names of the creators of the tree, like Allison Velsky, Lewis, someone. I can never remember the names. What is a self-balancing binary search tree? Adelson, Landis. Yeah, always get Landis wrong. Okay. But it's a self-balancing binary search tree. All right, so that means starting off with the binary search tree structure. Building of the tree happens the same way. New value. No, looks like I lost the front. There we go. All right, a new value be added from the root, going left and right based on existing values in the tree. All right, so with NEVL, after adding a value, work our way back up the tree and check on the balance as we go. An AVL tree will concern itself with the lengths of the subtree of each node on the insertion path. All right, so the tree is height balanced. the difference in the heights of the subtrees is no more than 1, then we're good. If not, we'll do either a single or double rotation, bringing the tree back into balance. All right, so let's build some binary search tree. Get rid of our checkerboard to a certain extent anyway. All right. All right, so before we get any particular height here, look at our first binary search tree here. And, right, so a leaf node, right? So if we look at the leaf node as a tree, right, it is a subtree within this larger tree. It is height balanced. Height on the left-hand side of the tree is -1. Height on the right-hand side, if I can get this size. Right, the height on the right-hand side is -1. So the distance between these two numbers is 0. Right, so a leaf node, obviously, there's no other possible way we can arrange a single node tree. It is just the one node, and that's all there is to it. When we look at the height of the 25 node, we'll have an empty subtree on the right-hand side, excuse me, on the left-hand side, and we'll have a single node tree on the left-hand side. That's the height of the empty subtree on the left, 25 is -1. And the height of the tree on the right is 0, right? Single node tree is the height of 0. Length of the longest path, right? And the height of this entire tree would be 1. We don't particularly care about the entire tree. We care about the difference in lengths, right? Are we leaning to one side or the other? And so at the moment we have a little bit of a lean. We're still within height balance because the best we could do is mirror this tree, have 42 as the root, 25 to the left, and we'd simply be mirroring the situation. So this tree is as height balanced as we're going to get it. All right, so if the tree grows and we add a new node off to the right, we're going to do a right insertion path to start. Right, this -1 value is going to go up, right? So we have -1 down here at the leaf node for let's see, make the value. I'll make it 71. All right, so the 71 node, this particular part of the subtree, right, is balanced as we can get it to be. Right, there's no other way. Not my little background's getting in the way here. Oh well. All right. Get my triangle back. Let's send it backward. Let's send it backward. Okay. All right, so this part of our tree is a subtree. All right, single node, that's as balanced as it's going to get. When the subtree grows up, we now consider control plus down arrow. Okay, let's see how well that works. Seems to be working. All right. All right, so triangle. Triangle, by the way, that's just a general notation to represent a subtree. That subtree might be empty. It might not be. Right, so we can pretend there's a triangle over here for the -1 subtree that's to the left of 42. That doesn't matter. This triangle represents this part of the tree, and it's a 2-node tree. Right. Yes, this number needs the tree. And on this path, the numbers need to grow up, and the same thing's gonna happen up here as we get to that part of the tree. And so as we work our way back up, we're gonna have this 2-node tree. And then 2-node tree is as balanced as a 2-node tree can be. We have a -1 on the left and a 0 on the right. Right, that distance on the number line between those two numbers is 1. That's as good as we can go. As the tree, as we keep going back up in the tree, right, we'll need to start adjusting for the addition, right? So this height, this tree is no longer a single node, it's now a 2-node tree. Height that tree is 1. So at this point, -1, those represents the heights of the subtrees from that node's perspective. Right, so now that we're at the 25 node, left subtree height -1, right subtree height is 1, and that is not happy from a height balancing perspective. See if I can grab the right thing. And just pick an extra number there. Okay. All right, so this 25 node is not going to be in a happy state. Okay, so in the above tree, 25 node, C is a height of -1 or 0 levels to the left, and a height of 1, okay, 2 levels to the right. All right, so the difference in the heights of our subtrees is 2, and we are out of height balance. Okay, so we inserted into the right subtree of the right node of the node that is reporting imbalance. We'll name the node as reporting the issue alpha. Alpha's child that was on the insertion path will be named beta. Since this is a right insertion, we'll do a single rotation, pulling beta up towards alpha, bringing the whole of beta's tree up along with it. This may require us to prune off a branch of beta and re-add it to the tree. Let's say off. Okay. All right. Let's cut clean pieces off the board here. Too much. Oh, no, actually, that was just enough. And slide. Send to Control Shift. All right. All about the shortcut keys. Okay, so here we have, this is our alpha node and our beta node. Beta is going to go up, which is going to elevate this entire right subtree from alpha's perspective. And alpha is going to slide down. So 42. 42 gets pulled up. Or another way to show it, 25 is sliding down. Let's fix our lines here. Close enough. Okay, so alpha is 42. All right, and our numbers are changing correspondingly here. All right, beta moved up. So we have 42 in the root. All values less than 42 are to the left. All values greater than 42 are to the right. And the tree is as triangular as we're going to get it. Nice, and back into a balanced state. We have a mirror scenario. Inserting into the left subtree of the left child of the alpha node. Again, the alpha node is the node that says, I'm not happy about what's been going on with my tree. Make this one a little bit of a bigger tree. And so as we go, we'll need to make sure the tree doesn't fall out of balance, because as soon as the tree falls out of balance, as we're building the tree, we need to immediately perform rotations to bring it into balance. All right. 41 come along. Add 27. Tree is still balanced. Nothing to do here. And if I add anything to the 27 subtree at this point, the tree would go out of balance. Not do that. So we'll add 67. We're still balanced. And at this point, we can add any node that we want. And the tree couldn't possibly become unbalanced because it's just going to be a leaf somewhere in this tree, right? You can add 1 or 40 or 88. Right? It's just going to be a leaf node somewhere down on the third level, and we won't fall out of balance. All right, so we will need to do a few insertions here. At 38, still in balance. All right, it's at 14. Are we out of balance yet? All right, not out of balance. How about if we add 7? We've fallen out of balance yet. All right, let's check. All right, so this is the newly added node. So we need to work our way back up. All right, 2 node tree, we're good. Check its parent. All right, we have 2 levels on the left, 1 level on the right, so we're still good. Let's go back up. 1, 2, 3 levels, 1, 2 levels, right? So tree is still happy at this point. All right, so as far as weight balancing, we may not be happy because we have 4 nodes on the left and 2 nodes on the right. But as far as height balancing is concerned, we're still okay. We can actually go a fair way before things come out of balance here. Okay, we'll add 22. This dark mode messes with me sometimes. And then we'll go ahead and add, let's go for 17. All right, first and foremost, do we still have a binary search tree here? Because, yeah, it being a binary search tree is kind of an important detail. All right, if I try to add 71, obviously 71 couldn't fit here. It has to be parent, grandparent bound to be in range. All right, so work our way up the tree. 2-node tree, balanced. This tree here, we have a height of 0 and a height of 1, so we're good. All right, so we work our way up the tree, going back up. All right, so we're now looking at 27's children. Here we have a height of 2 on the left, a height of 0 on the right, or 3 levels versus 1 level. So we're going to have a problem here. We're going to report an alpha node. Alpha node. Oh, and then let me change my data point here. Add it to the wrong subtree. I want to make this an 11. Otherwise, I'll be getting ahead of myself. Okay, then we'll have beta. All right, so we inserted into 14 subtree, specifically on the left-hand side. All right, the left subtree of 14 is where we added our new value. So beta is going to rotate up towards alpha. That's going to push 27 down. 38 is going to go down with it. 22 is going to lose its home for a moment here, right? Because right now, 14 has 22 as its child, but 27 is going to become 14's child. Right, but the relationship's going to hold, right? This one's going to fall off. Its parent is 14, grandparent 27. It's still going to have the same ancestry. It's just 27 will become the parent, and then 14 will become the grandparent as we do this rotation. All right, so we will do our rotation. All right, the 27 subtree will move down. 14 subtree will move up. And I lost my background. I meant to cut that, but I deleted it. All right, so this old edge, right, that doesn't work anymore. 22 is floating off. All right, so 41 was the parent of 27. 14 is being promoted to take over its spot. Close enough. All right. We'll be reattaching. And so until we still have 22 to worry about here, but at the moment we have a binary search tree. 41, all values less than 41 are to the left. All values still great, right? This part of the tree did not change, so not much to worry about on that side. And then we have 22. All right, there's only one place 22 can fit here, and that's between 14 and 27. 27 formerly had 14 as its left child. So we're guaranteed that there will be a spot here for 22 to be picked back up. All right, so we had to prune it off the tree, and we'll splice it back in here where a vacancy was just made when 14 stopped being 27's child and instead become its parent. And that gave us space here, right? So now we can cross check. All right, we have this 3-node tree. That's good to go. All right, 2-node tree. It's good to go. 14 sees 2 levels on either side. And then 14 says 3 and 2 levels. So we're nice and height balanced. All right, we did that with a single rotation because we had a left insert. Now, let me point out one thing here. A mistake that people will often make, and they will try to make 41 the alpha node. While 41, if we were to go that far up, would be complaining about the heights of its subtrees, right? We have 2, 4 levels and 2 levels, or a height of 3 and 1. Fixing things up here is not the right place. We want to fix it as low in the tree as we can, so we work our way back up from the insertion to find the reported imbalance, and then we fix it there, because when we do the fixing here, as we saw when we go to the next tree, right, that makes the 41 node happy in turn, right, because its whole left subtree got shorter when we were making the 27 subtree shorter. So 41 is no longer complaining about there being a height of 2 on the left and a height of 1 on the right. Questions about that at the moment? So what would the number height look like here? The height of this tree, the 41 tree has a height of 1, 2, 3. Right? It's the lowest level. It's the length of the path from root to the lowest level of the tree, which there are 3 paths that we could make. 1, 2, 3 hops. All right, so alpha. All right. Alpha. Where is alpha? Okay. Let's bold alpha, shall we? Is something of keyword there. Right, alpha, beta. Right, alpha is the node that we found when going back up the tree after inserting that detected an imbalance. Beta is the child of alpha on the path that the insert happened. Well, we can add the stat here. Add details. We have height. 41 tree is 3. Height of 14 tree is 2. And the height of the 67 tree is 1. So the difference in 41's subtrees is only 1. So we're back into height balance. Right. 1, 2, 3 for height. Left subtree. Sorry, height of the tree. The longest path is on the left-hand side, right? We only have 2 over here, so this subtree isn't contributing to the height of the tree. If we keep adding on the left-hand side, imbalance will ensue, and we'll have to start pulling people up again via rotations. Answer the questions. So single rotation may not be enough. We're following a path that goes right to left or left to right. From alpha's perspective, then we'll have to do a double rotation. A single rotation will just mirror the problem and we'll still be out of balance. Let's see, question. So when the difference is equal to or less than 1, the tree is balanced. Yes, height balanced. Yes, the height of an empty tree is -1. So a height of a single node tree is 0. Height of a two node tree would be 1. The height of a four node height balanced tree would be 2. Three node tree would also be 1 because it'd have to be a triangle for it to be height balanced. All right. Double rotation. And I'll keep it small to start and make it a bigger tree afterwards. And if I get a sequence of values, 54, 71, and 63. So 63 is the most recently added value. It's the only leaf in the tree, so it has to be the most recent one. Two node tree, of course, we're good. When we get to 54, we have a height of -1 on the left. -1. And we have 1 on the right. Distance between these two is 2, so we are out of balance. So we have to do some, well, let's do some coloring here first. So we're going to have alpha, going to have beta, and we're going to have gamma. And these are just names. Alpha is the node reporting imbalance. Beta is the child of that node on the insertion path. And we'll have gamma as well. Greenish for gamma here. Who is the grandchild of the insertion path here. So what we're going to be doing is 63 is going to rotate twice. And we'll rotate to 71, pushing 71 down, and then I'll rotate again to 54. Right, if we try to do a single rotation here, try to bring 71, 54, 63 would have to be pulled off, and then it would become the right child of 54 for it to still be a binary search tree. So it would just mirror the problem, not solve anything. So we're going to have to do 2 rotations. First rotation. 71 will move down. 63 moving up. And so at this point in time, we still have a binary search tree, but it's imbalanced. All right, alpha is still complaining about the length of the right subtree versus the length of the left subtree. But we have, after our first rotation, our single rotation scenarios. So we can kind of use 71 as the new node here, and it's in the right subtree of the right child of the alpha node. We can rotate again. 63 gets pulled up. And we will adjust our heights to 0 and 0, giving us back into a height balanced state. Recordings are posted in Discord. I want to say it was posted last week. Let me cross check. Let's see. Yep. It lives in YouTube now. It is now forever space. Yeah, there's a recordings channel in Discord. All right, so 63 was the gamma node. First rotated towards beta, then rotated towards alpha, giving us a nice triangular tree. And when we have a triangular tree, our own notations, get that nice logarithmic time. All right, so double rotation was required. We rotated gamma towards beta, and then rotated gamma towards alpha. As before, subtrees may need to be pruned and then spliced back into the tree. Into the tree, keeping the ancestors at the pruned branch had previously. And do this again with a bigger tree. Question, if I rotate gamma towards alpha, how come alpha doesn't just become a child of gamma? Well, it does after we do the next rotation. Our rotation has basically a set number of instructions to change the parentage, because there will be other node links to keep track of, right? Because the 55 node may well be a subtree of a larger tree, right? So there's going to be links pointing to this node that need to be tracked as well. So it happens in two steps where you can do a rotation, right? Tell the node to do a right rotation sort of thing, and then tell it to do a left rotation. And it's the same algorithm as it would be for our single rotations, where we say do a right rotation, right? Geeks for Geeks has the code. We'll take a look at that. Have to reduce some more. Building. Oh, there we go. All right, let's build it. Build a bigger tree. Ooh, lag. What's going on here? There it is. Wow. Okay. Get a pop-up earlier complaining about my connection. So let's see how things are going tonight. So far, so good. It's always good when we don't lose packets. Like them all to get there. All right. I said copy, I said paste. There we go. All right, so let's toss some numbers in here in a minute. All right, so if I write a node down here at this point, this tree would be unhappy. So add one over here. Try to keep things on the happy side. All right, so we're more or less getting where we were before. Our goal is to get this node to be unhappy, so we're going to do this subtree and then this subtree. Somewhere down along here. All right, let's get some data to our nodes. We link things up. All right. Links, links, links. I'll have to double check that I actually built it correctly as I went, because if it had fallen out of balance before we got to this state, then we would have had to do rotations already. All right, so 57's on its way in. So before 57 gets here, to make sure that we're still balanced, right? 3-node tree balanced. 5-node tree here. Right, it's as balanced as can be. Height 2 on the left, height 1 on the right. Over here we have height 3 on the right hand side, and we have a height of 2 on the left hand side. So 57, right? Any data point between 48 and 68 will cause us to fall out of balance. If the value is less than 54, we would have gone into a left-left scenario, so it would have been a single rotation. Values between 54 and 68. Yeah, right, so 57 or 61, either way, we'll get to the right subtree of the node that's going to be unhappy. So we'll have our alpha, beta, and gamma situation. So let's link that in there. All right, so we'll cross check, right? 2-node tree is happy. Our 4-node tree is happy. When we go up to the level, right, we have 3 on the left, just 1 on the right, and that is no good. So we will have rotations to do. To get us back into a happy state here. All right, so our first rotation. 60 will find its way. I can grab everybody, moving on up. All right, as you can see, 57 is going to have to get lost track of for a moment. And we will need to reattach. All right, 6 is getting a new parent. 57 is loading in space. And we can go ahead and reattach. All right, so we have a binary search tree still. Right, it never stops being a binary search tree as we do our rotations. So check your work as you're going. Make sure things are still a binary search tree as they go. Right, so our first rotation. Let's add a text box saying that that was our first rotation. The Discord link is on the syllabus page. After first rotation, I think it's still good. I think I made it for 3 days. It might actually be expired now at this point. Might have to make a new one. And we'll go ahead and do our second rotation now. All right, that's going to move up. These are going to have to move down. So 68 will have to slide on down for us. And then all this goes on up. And we'll have some links to fix here. Got that. A little OCD here. All right. And get our links fixed. All right, let's cross check. We still have a binary search tree at least. All right, 48 at the root. Everyone less than 48 to the left. Everyone greater than 48 to the right. 60. Everyone less than 60 to the left. Everyone greater than 60 to the right. All right, and so on and so forth. Our data relationships are good, and we can cross check. All right, cross check our heights, right? 3-node tree, happy. We've got a 2-node tree here, that's happy. And then we've got into our larger tree, right? It's almost a perfect triangle. All I need is one more node here to be good to go. And then we can go up further into the tree here, right? 2 to the left, 3 to the right. And we're back into a height balanced state. All right, so you want to trace the line to the node that was inserted back to the root, then checking the heights on those from the leaf node that we just created all the way through the subtrees to the root. If everyone says they're happy with the heights, then no rotations would be required, and we're good to go. Ready to move on to the next insert. All right, so since the tree is height balanced, inserting the tree is going to be big O log n. And then lookups. In turn will be big O. I'll link to the doc. Wow, my eyes are going bad. I read Discord. Since we were talking about the recording earlier. False association, right? Not necessarily every check is going to eliminate half the tree, but it's going to eliminate a proportion of the tree close in magnitude to half the size. All right, first test eliminates left subtree of 2 nodes plus itself. Next test eliminates 2 or 3 sub nodes plus itself, right? We're eliminating close to half as we go. So we'll have logarithmic time for our operations. So an AVL tree, just like the binary heap, will have logarithmic times because binary heap also enjoys being a balanced tree structure, and being a balanced tree structure is going to be a requirement to get those logarithmic times. Mm. Get my numbering up here. All right, that's up there now. Let's see. Next tree structure. Any questions about AVL at the moment? B tree, note that the B does not stand for binary or anything for that matter. It is going to be a balanced tree structure. Oh, we're going to talk about the code. I knew I was forgetting about something. All right, RAVL tree code. Right. Yes, lovely drawings here. Doing our rotations. Right, left rotation, you can see beta is going towards alpha here. We should call them ABC. Right, just names. Yes, bookmarks. Let's talk about those bookmarks later. Let me open up those tabs on the side so we can talk about that later. Right, multiple rotations. Right, the idea is to get from a linear-ish looking structure to a nice and triangular situation. What do they do? Hide the code. Do 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 do. Introduction. I guess I just pulled up the wrong article. Do 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 do. Here we are. All right. Node class. As you can see, it's much like what we've seen before. You can see that do add a helper per height because having to persistently recalculate how tall of a tree you are over and over again when height is a very important characteristic is going to be inefficient. So we want to track the height as we go. Couple helper functions, and then we have a right rotate. Right, so passes a node along, grab a left pointer, or grab a right pointer, go ahead and do some pointer alterations here, and then do some height updating. Right, so pointer manipulation to repoint arrows. And we have that was the right rotation. Then we have a left rotation, which you'll see is pretty much the same thing, just slightly mirrored. Right, grab onto a right node instead of a left, and grab onto a left instead of a right. And right, update the left instead of right, and right instead of left. Update the heights. Right, and then the top level logic. Right, inserting stupid ads, making things move around here. Right, so step one, we need to insert it somewhere. Never been a particular fan of this style of recursion because we don't need recursion. I definitely recommend if you don't need recursion, you guys are not. If you're in a linear problem, right, we're only going down a branch, then I would avoid recursion because recursion complicates things a little bit. Anyways, it does the insert, right? Gets the heights, checks for balance. Right? If we are out of balance, we're either going to do a rotation to the right or a rotation to the left, depending on was it a left, left, or right, right scenario here. Otherwise, we're going to do multiple rotations. Right? So we call a left rotate on the node. After that left rotate's done, it assigns it back, right? Fixing your child relationships. And then a right rotate again on the nodes. All right, so if you want to pull this code down, step through this code, Try to give you a better picture. I don't know if that'll give you a better picture or not. I think it's definitely a good one where it's pencil and paper is the best way to visualize things here. But right, we call this the two functions we talked about earlier. Either swapping some pointers around, parent, child, fun stuff, in a right left, or in a left right, or our more complex case. But you can see the code isn't all that much more to it. Sometimes the code's simpler than the concept. Not always the case. Now I can post a link to it. You will not need to be coding anything for AVL tree. Now, when you take advanced data structures, that story might change. You'll probably be coding either B trees or AVL trees. Where's the file structures? Yeah, the thing is, when you get to file structures, then you might be coding it. For B trees, because B trees all often live on disk. Because a database is going to be making use of this particular tree structure. All right, so B trees are a balanced tree structure. It's an n-ary tree. The B tree will have an NM specification where n is the minimum number of children and m is the maximum number of children. Smallest B tree that we can use is a 2-3 tree. All right, so 2-3 B tree. A non-leaf node has either 2 or 3 children. Second. Okay, so its ordering mechanism is much like a binary search tree, a left to right pattern. Except for breaking it up to multiple ranges. All right, so we're going to have in a 2-3 tree, our node will support 2 data points. 1 second. All right, so 2 data points. 2 data points will allow us to break up a number line into 3 sections. First section, all those values less than the first data point. Second section, values between 2 data points. And the third is greater than the second data point. Node 2, 3. Right, so we would have int data 1, int data 2, and we would have our node 2, 3, start link 1, 2, and 3. All right. So I think we're more B-tree node, more general purpose node structure. Ooh. Would be just an integer array. And a node array. Links type thing. All right, with a constructor that would set. All right, we'd have helper fields here, so we would know what our range min and max are. But this is as simple as we can make it. So we'll have data 1 and 2 cleave our 2 sections of data in. All right, so building a B tree. All right, so we're going to look for a leaf. So we're going to look for a leaf starting at the root. The new value is less than data 1. We'll want to add to the first subtree. Else, if less than data 2, we'll add to the second subtree. Otherwise, adding to the third subtree. All right, so we will dig until find a leaf. On finding a leaf, add the value to that leaf node. There is space. If not, we'll promote the median value up the tree. Smallest value stays in the node. Largest value gets put into a new node. It's a sibling to the existing node. Existing node. All right. Drawings. Worth 1,000 words. Possibly thousands of words. All right, so we will draw the node structure is like this. Data points go inside the boxes, and the vertical edges are the links to track subtrees. All right, data to add. Just go ahead and add whatever. 1, 2, 3. Well, we'll do 10, 20, 30. Gives us more room without having to go to decimal space. Okay, first add empty tree. Create a node. Drop the data point in, and we're done. All right, so we have the 10 subtree, or 10 tree. Next data point. So we have existing 10. We go to the first node, and we will see that it is a leaf. Now, the way that we test to see if a node is a leaf is we'll look at the first pointer. If the first pointer is null, then this is a leaf. The way that we're going to keep our data organized in here is data, if it exists, goes from left to right because we have the data mechanic of values that are less than data point 1 are in the first subtree. So we're not going to just have values strewn about in the array. They'll always be filling from left to right. So we found, I forgot to add my root name here. All right, so we started at the root, found the leaf. There's room for the data point, so we'll add that data point in. Okay. Next data point. We want to add 30. Right, we don't have room for 30 to go into our tree. We started at the root. We found that the root is the leaf. Try to drop 30 in, but there wasn't space for 30. So what we have to do is we're going to have to grow the tree. Right? B trees are going to grow bottom up. So what will happen here is a new node will be created. The largest value will be created in that new node. Show us the new node over here. And we have 20 being promoted up the tree. Right? Since there is no up the tree at the moment, we are causing the root to split. A new root will be created. And the value that was being promoted up will be promoted up the tree. And we'll go ahead and link the trees here, right? So we have link 1 points to the subtree. The value is less than data 1, which is 20. So we have 10 node over here to the left. And second data point, second link, values greater than 20 and less than the second data point. There isn't a second data point, so it's just values greater than 20. At this point in time, so we have a 30 node over here. All right, next step, need to update the root to represent the current state. All right, so our pointer updates to track the root, and a newly named node is no longer important. Yeah, project T from the console. What does it say? Let me double check what it says. It should just say from the console. I'll use a file because I'll just do console redirection. But it should not be reading, it should not be saying from a file, right? There's simple test data that you could just drop into a file like I showed you last week or the week before. Right, I did show this class console redirection, right? Or am I getting my classes mixed up? We can have a test file and have it pretend to be like it's a person typing at the console. Is that ringing any bells? All right, we'll have to do that again tonight. Yes, remind me if I forget, because I have propensity to forget. Okay. When we get to that, keep building up our 2-3 tree here. All right. Clear some space. Nope. All right, so 40 is up next. Start at the root. We see that the root is not a leaf because it has the first pointer not null. So we'll compare 40 to 20. We see that it's greater than 20. No second data point. So we work our way down and we find this leaf node. It's a leaf, and the first pointer is not pointing to anything. So 40 will go ahead and insert. And you'll note that it is inserting in sorted order here. We have a data relationship. Less than 30, between 30 and 40, and greater than 40 if subtrees will grow below this point, or rather grow up as data points move up. But there was room for 40. So the inserting was nice and easy there. 50s want to come along next. Following the same path, greater than 20. Found the leaf node that we want to put it in, but the leaf node does not have space for it. All right, so we will have to do a split as we did before. Get things lined up close enough. All right, a new node will be created. Create a new node. The largest value, which might be the value we just added, might be a different value. But that value goes into newly created node. The median value is promoting itself up the tree. All right, so we have a newly created node here. Newly created node with 40 working its way up the tree. All right, so 40 is going to find its way to the root. The root has space for it. And now we have a 40 data point. We have 2 data points in my node. And that gives us enough to track 3 children. Okay, so important note. Important. If a non-leaf node has a single data point, then has 2 children. If a non-leaf node, right, aka an internal node, has 2 data points, then it has 3 children. This is the structural requirement of things. Also note data values will left to right if there are fewer than the maximum number of data points in the tree. They fill from left to right, and consequently, children will do the same. And so if you look at our trees here, right, we have a internal node with 1 data point. First 2 links are set. We have an internal node with 2 data points, and then all 3 links will be set. And you'll never have like a missing subtree over here. Not going to happen. Where we have a link off the left, link off the right. That is not a valid 2-3 tree. Right? So it's either going to be 2 children, the first 2 pointers, or it's going to be 3 children with all 3 pointers or internal nodes. All right, let's keep on building our tree here. Okay. Cut that out. All right, 60 data point. Next data point being added, greater than 20, greater than 40. So it comes down the third branch, find the leaf, insert it in order there, and then we're getting done. Let's add another data point, 70. All right, 70. It's going to cause a lot of change here, right? Greater than 20, greater than 40, follow third branch, find a leaf, the leaf is full. 70 wants to go into this tree, but we don't have space for it. All right, so we're going to create a node, subtract the largest value, which happens to be the value we're inserting. So I'll have the new box over here. All right, let's get rid of that extra box. Our 60 data point is going to be working itself back up the tree. All right, so it's working its way up. Back up the tree. Uh, okay. So 60 is trying to do the same thing as we did before with our leaf nodes, trying to insert into the root node, but we don't have space for it. So we're going to need to create another new node for 60 to take its place. So creating a new parent node. And before we go further, what we want to do is start fixing some links here. All right, so this is going to be a one node. One node, one data point node. So it's going to have two children, and we have 40 being promoted out, right? We're splitting this node. So it's the same thing as when we were splitting a leaf. Internal node will go through the same process. Largest value gets split into a new node. Smallest value will stay in the existing node, and the median value will be pushed up the tree. And so before we push 40 up the tree, let's fix our pointers because there's only a single data point in the former root. So it can't have all three of these children, right? So this third child can move on over to be the first pointer, 60, right? 60 points to the subtruth, values less than 60. And our newly created node needs to be brought into the tree. So we'll go ahead and link that in there. So right now we basically have two little B trees, right? Both of these are 2-3 trees at the moment. If I look at this one, we have 20 with 10 and 30 in it, and we have 60 with 50 and 70 in it. And then we have 40 growing its way up. Right, I just split the root. Splitting the root is how the tree will grow taller. Interesting preview. All right, data's there. Let's get that box out of my way. All right, make some space for my new root that's about to pop on top. All right, so a new root gets created, taking on the value that was promoted. root. And this newly created node will want to point to the existing root and to the new parent node we just created previously here. And so the old root is gone. Clean up our names here, move our root pointer up to 40. We don't need this named parent pointer and that new node there. And we can just move this over to make it somewhat better looking. All right, and it's balanced. We might have some sparseness, right? So this is pretty as sparse as a 3-level 2-3 tree is going to get. We have 7 nodes. Still have a nice growth here. We have 1, 2, 4. Right? The next level will have to have at least 8 nodes in that level to be a 2-3 tree, but could have as many as 27 nodes at that level because, right, we can have 1 to 3 to 9 to 27 at the next level of tree if the tree were to grow that big. All right, so it's balanced. Since it's balanced, we have logarithmic times and database indexing would make use of this structure. All right. And we'll disregard the statement in question. It's always good when you answer your own faster than I can even see it. All right, so just briefly talk about database indexing. Let's say we have a database with a small table, only 1,000,000 records in it, medium table. It's all relative depending on who you talk to, right? We do payment processing. We do about 30, 40 million transactions in a day amongst our environments for our payment processing, and we're definitely not the biggest payment processing entity out there. Definitely larger entities out there. I don't know how many billions of transactions Visa, MasterCard, or if we go all the way up to the card brand levels, they do on a daily basis, but there's a significant volume. And if you're trying to cancel a transaction, right, you dispute a transaction or whatever, so that was done in error, you're just trying to find details of that transaction. I'll get to your question in a second. We need to be able to find data quickly. And this data is so massive, it's going to be on disk somewhere because there's not enough RAM to store on billions of transactions and things like that. So we need a fast way to find the data. And in a database index is what helps manage things for us there. The database index is basically a data structure that sits on top of the database as a separate entity, and it tells us how to find data. So we would use these data points to possibly pull subparts of the data with us if it's a covering index, or basically where on the disk system to find particular data records so that we can get things quickly. Right? Say we want to do, right, so we're just doing some website that requires you to have a user account in order to gain access to various bits and pieces of the content, right? Say we're going to your bank website, right? You log in, username and password, they're going to look you up in their database, and if all they had was a simple database with no indexing on it, and they had to do a scan on the database table, right, which is basically a linear search, right? A linear search is not good enough when you have a lot of records. And I'm not quite sure what the threshold is for a linear search, right? Because if you only have like 10 or 20 records, linear search is probably going to be just as fast as a binary search. Binary search does have a little bit more overhead per iteration. to figure out where to go, left, right, sort of thing, than a linear search does, which just start going down the list. Right? Linear search doesn't have the precondition of the data being ordered in the first place so that we can even do a binary search. Right? But beyond that, I have a million users in my system, and every time one of them wants to log in, I have to go look them up in the database, and I have to do a table scan, a linear search on the database. Right? That's going to be very, very slow, especially since we're talking about disk. And disk is almost always the slowest part of an entire computer system. And so what we would do as a developer is we would build an index, or maybe the database administrators are doing this for us because they're seeing bad performance. They wouldn't create the index on their own, but developers should realize it in the first place. Build an index on your usernames so that we can much more quickly, because we can go ahead and load up this tree that represents the usernames in our system, because a million element tree in memory was just the usernames, not the entire user records with all the details associated with that, is going to be much faster to get through. And maybe we're not loading up all million records, but rather ranges. Right? These might be the key fields tracking us. Okay, we have the first 10,000 usernames go up to Bob Smith type thing, and then we got 30,000 usernames go up to, like, you know, Joni Smith or whatever, so on and so forth. So we know which particular subset of file to work in, right? So anything that we can use to divide and conquer, break the problem down, break the problem size down to smaller and smaller pieces, the faster things will go. All right, so the question is the reason why we made 16 to its own leaf. Right, so 60 got its own node because 60 tried to get inserted into the root. Right, so 60 was trying to go into here, and the root did not have space. So the largest value, whatever it is the one that gets go into its new node. Right, so it's purely mechanical. So if we insert, as we build more trees here, which we'll definitely build more trees after we take a break, we'll see which values are moving along. So let's go ahead and we'll take 5. And then we will continue building some more B trees.
Professor.
Yep.
I had to step away for a second, but I heard that there was something you needed to show us for program 2.
Yes. We'll do that in the lab section tonight. How you can do IO redirection to simplify testing.
Okay, yeah, because I was having trouble calling. I thought we had to call the .txt for names, so I was having trouble with that.
Yeah, we don't want to do any file IO, just console.
Okay. Thank you.
Okay. Let's build some more. All right. We'll add in 40 to start. Next data point, we'll add in 20. 20, we'll push 40 to the side. Guess I did forget to mention root. All right, this time we'll add a central value. So we'll add 30 in. We try to add 30 to this tree. We found a leaf node, but there's no room for 30 in here. And 30 wants to go between 20 and 40. Whomever is the larger value, the middle value promotes up. And that middle value happened to be 30. That newly created node become the new root since our root is what split. And it'll keep track of the already existing 20 node. And so we had the 20 node originally. 40 got split into a new node and 30 promoted up. All right, so any new value at this point, we'll find a leaf. All right, let's add 17 next. 17 pushes 20 to the side. And then we'll add next 5. 5 is trying to be added to the tree. All right, we start at the root. 5 is less than 30. Go down, found the leaf, insert the value into that leaf. Leaf doesn't have space, so we're gonna have to split things here. So a new node. Will get created to handle the largest value. Uh, Right, so we have 5 will actually get inserted into the node. 20 gets dropped into our newly created node, and 17 is working its way back up the tree. All right, so we had 5, 17, and 20. Smallest value, even though it's the newest value, stays in the existing node. So this is our existing node. 20 is our new node, which is why it's not linked into the tree just yet. And the median value is promoting its way up the tree. All right, we'll keep things in order here. 17 goes before 30. 17 found its way up the tree. When the 30 data point is moving over in the root node, the corresponding pointer will move along with it as well. This is a 2-3 tree. There's no such thing as a 1-2 tree. That's basically a binary search tree. All right, so as the links stand, we have subtruth values less than 17. We have the subtruth values greater than 30. And we have our newly created node here that's waiting to be linked in. And it has the values between 17 and 30. So we'll link it in. All right, so our 2-3 trees at a 3 state for the number of children for its single internal node. And if we keep on growing, all right, which leaf do we want to build up? We want to build the 5 leaf, the 20 leaf, or the 40 leaf? The 20 leaf. Okay. So value that'll go into the 20 leaf will be something between 17 and 30. All right, so we have 25 come along. Greater than 17, but less than 30. So we follow the second branch, found the leaf, drop the value in, sorted order. If we go ahead and add another value, say 27, unless someone has a different value that they'd rather have. 27 comes in. All right, we won't have space for it. So this node will split. And the node splits, 20 stays where it is, 25 works its way up, 27 goes into a newly created node. So these folks shift over a bit, make some space. Waiting for it. Okay. All right, so 27 into newly created node with 25 working its way up. All right, 25 does not fit in the root. So we're going to have a split happen here. 25 is going to be the median value. So it's going to keep working its way up. 30 goes into a new node, being the largest value. And since that value moved, just as before, we had to adjust pointers. We will adjust pointers again. All right, we still have our newly created node here that was waiting for a home, so we can go ahead and set that link now. All right, it's like we had before. We have a tree, 17, 5, and 20 in it, 2, 3 tree, and a tree, 30, 27, 40. And we have 25 working its way up. 25 working its way up. New node, new links to be set. And we will update our route to match. Question. So when adding to a full node, the older value goes up. And it's not about the age, it's about data relativity. Ew, what happened to there when I did that movement? Ah, 40 was not quite moving along with it. All right, get the brick back up there. All right, so doesn't much matter what the new value is as far as to the restructuring is concerned. All that matters is what the new value's relationship is to the existing data points in the node that it's trying to squeeze in. If it's the smallest value, it's going to stay. If it's the largest value, it's going to end up in a new node. And if it's the median value, it's the one that's going to be promoted. Whether that is an existing node, this existing data point or a new data point, that doesn't matter. Median always promotes. Smallest value will stay in the existing node or be inserted into it if it is the new value. So it'll basically push out the largest value. So the largest value gets pushed off the end of the array. And as it gets pushed off the end of the array, it gets dropped into a newly created node. And then the median value promotes up. And the same thing would be true if this was like a 3-5 B tree, which would have 2 to 4 data points in it. Right? 4 data points can get us to be able to break space down into 5 sections. And then we'll have multiple data points down to leaf level. Right? And on that note, when I was saying that database indexes use this tree structure, we were talking about B trees, and the NM is going to be a much larger scale, right? And the scale is going to be dependent upon the data that we're actually pushing things into it. At least it is in SQL Server. SQL Server has an 8K page size, so it likes to make things fit as well as they can on that page size. So the number of nodes could vary from table to table index. Yes, so the smallest value will stay in the leaf node that's being split. Greatest goes into its own, and the middle value gets promoted. Yep. Middle, also known as the median. That bit of concrete in the middle of the road. Let's see, let's see. What else do we need to talk about for B trees? If you take I forget which database class it is, but one of the database classes gets into this in further detail, and we are doing a simplified version of the B tree. Real heap, binary search tree, traversals, binary trees. Okay. All right, let's talk about the lab. Let's see. We had some tree labs due. A bit of grading to go here. Looks like we're still missing about a dozen. We have a little bit late questions to ask about the binary search tree. All right, still turn things in. Late penalty is applying. The later you turn in, the heftier that penalty. So it's always best to get them done as quickly as you can. All right, our array-based tree. So we got better progress on that one. That's good. All right, we'll go over the code for these guys later tonight. Again, during the lab section. Min heap. Probably save this one for next week if you want to look at code for that one. Heapify is a little bit of a fun function to add for bubbling values up and or down. And our traversals. Once you've done one, the others are easy to go. All right, let's talk about a little of automation. String name, wait. Less than 15 plus. Uh, name, CN name. Why are you capitalizing it? Silly website. Whatever. We'll just make a basic list here. Plus person. Create a name. Create a wait. Person node. Which has a person. A person. Make it a pointer, whatever. We have our next pointer. And let's make everything public. As lazy as lazy does. All right. Person list. No, ints are sufficient. I track my weight to the decimal point. So I kept that here as well. All right, so our person list. Our head node. And this will just be a single linked list where I'm not actually doing program 2. I'm just doing the gist of things here. Everything's just going to be pushed to the front. Let's see. We've got an add function that takes a person. Well, we'll just have to take a name and weight, and I'll just create the person on string name, float weight. Person per. Close new person. All right, per name, per weight. Same. And we're creating a node. Equals new person node. And our node person equals per. Node next equals head equals node. All right, and we'll have a print function. All right, so this is just stack-based operations just to have some sort of output. A person node. Temp equals head. Well, temp. spit out details, name, and some weight. And temp equals temp. Next fun stuff. All right. Person list. And name weight. And we will print. All right, so I'm testing this code for 15 people. Assuming I didn't have bugs. What or anything. Ah, yes, temp person name. Let's see, what other bugs might I have? Stupid autocorrect. It's private. Oh, so it is. I forgot my public. Access modifiers. Oh, just being, I mean, it's not the homework code, so I can share the link to it if you want. Let's see. I see the questions. Do we need a person class? No, you don't need to, but it's separation of concerns. If you haven't, I recommend reading this. This is a very very good subject. Might be a little bit earlier. It's on the software engineering side of things, but single responsibility, S part of solid. All right, single responsibility. You want classes to be as small as you can make them, such that they're not trying to tackle the whole world. So that's kind of what I'm doing here. Right, I have a person who's right for to create a string representation of it, all that other fun stuff. Right, keep my classes small. Class is small. This class as small as you can keep it, sort of thing. What lab we're going over? We're going over how to try to automate testing, and I'm using code that is kind of sort of like program 2 to go over it. All right, so what's my current bug I need to fix? No bugs. All right, right. Bob 2, Tina 3, pain, especially with the lag I'm getting, but try to type all this stuff over and over and over again. All right, so it'd be so much easier if we just, kind of automate that to a certain extent. Where's my program 2? Program 2. There we go. It's lovely. Test data. So in an online compiler, right, there's this text option for input. So we can run the code and it will just feed the text. Right. You can see it does kind of corrupt the output a little bit because it's basically redirecting input. But Mark at 150 got added. Then we have Tina and Mark, right? So I can test my code. Oh, there's a bug. I should have been putting things at the other side or one side versus the other type thing. And I can just change my codes. Like, oh, I wanted to dash here between people's names, sort of thing here. And I change my code just to tell it to run. And right, and it runs. So Visual Studio, copy my codes, bring up our data structures. Percussion, is this actually the file that's in here? Yes, it is. So we'll build. So I have an executable. All right, so for on Windows machine, x64 folder, debug, right? We have our program. So if we double click our exe, right, we have our code. And wrong code, wrong code, wrong code. Data structures, there we are. Bob, 123, right? Tina, well, apparently I managed to crash it. That's interesting. Bob, one. Ooh, my loop is looping here. Yeah, slight problem. Different browsers here. I didn't initialize things to null, and it's not quite going to null, so it's blowing up the Stack Overflow. All right, let me fix my code. Let's see, we have questions here. Yeah, Wikipedia is actually pretty good for data structures. How we sort the names weights. We'll get to that in a second. Where my code? This is not doubling request. I'm using a stack. I created a stack. Right, this is not program 2. All right, let's see. Need to explicitly set things to null here. Do 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 do. All right, node. Do 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 do. All right, let's add a constructor. Do do do. So that next equals null on the very first time. Let's build that. Get a new binary so I can run it without it stack overflowing on me. Stack. Oh, it's still dying. All right. Temp equals temp next. Someone's not coming up here as null like I wanted to. Let's find out who it is. Let's run the correct program. And we will find out who is not nulling. Null, 1, 2. All right, temp. Temp next is going to C's. They're still going to C's here. This is terrible. Mm-hmm. You are going into my person node here, aren't you? 1, 2. Yes. Temp next is null. So we got our person node. Oh, I don't put the constructor for head. Okay. And person list doesn't have a constructor. Just set head to null. All right. Get back to my numerous windows here. Null is found. Maybe not. I did build it, didn't I? Thought I did. One, two. Oh, yeah, heads null. Okay. Heads null. Head is the node. Head next is null. That's good. So let's go on my print. Temp is head. Next is null. All right, temp. Right out. Temp is null. Stop looping. All right, that's good. All right, must have a stale binary. Let's try that again. Finally, right, but right, so typing 15 people, right? That's no good. So we'll do the same thing here, right? We have, I guess where I showed this last week, but anyways, let's show it again. New text file. People.txt. And we will drop in some people. Copied in, quite take. Let's try again. Copy. All right, so I have my data file of people. So when we go ahead, right, one of the things you can do, you can actually drop files onto an executable. Ah, it's not quite working. Fine. I used to be able to get that to work. Let's go get a command shell open. All right, so we have our program. All right, call out the command line, run here until we break it. Okay, because here's not a number. What we can also do is use some DOS. Get that bigger here. All right, use the less than. So it'll redirect this text file as the standard input. And it will run our loop, pulling people in and printing out. All right, so now if I have a bug, no, I don't want that dash. I want a colon instead, right? All right, make a simple change. Change your code. You should test your code, right? There's too much white space. Build it. Make sure my executable actually gets there, right? It's built. Come back, hit the up arrow key, run it again. All right, now we have a whole bunch of fun, lovely colons. All right, so automating testing is a very, very big thing. We're not going to go so far as, well, maybe at the end of the semester in C# if you want, I can show you unit testing. This is where you write code to test your code so that you have high confidence that every time you change your code does what it's supposed to do. But this is one step closer, right? Make your test file. Make your test file, and then you can plug it in against the code and see that it's producing expected output. Is there used to be a C# class? Do we not have one this semester? Chan's teaching it. All right. Yep. Yeah, I went down to one class a number of years ago. Anyways, this semester's a little bit of an anomaly with two classes. All right. The the prompt, yeah. The console window. Do I need to do some rewording here? All right. Yeah. Read from the console. Read day names from the console. Names on a line, followed by wait next line. Right. The prompt is something you would see at the command shell. Right. So this is the command shell. So this is the prompt sort of thing. Do do do. All right. And int's fine. You can see my test data is all using ints. Ints are perfectly good. As mentioned before, the data itself is not something we particularly care about. It's the organization of the data that we care about. You don't need a command shell for it to work, right? It's console-based application. You can build it and run it by double clicking on it, just like I did. Right? It's an exe. Or I can run the other classes code site sort of thing, right? Double click and run it. If you have a little problem with being able to see what's on the other side, when because in most console-based applications, they just terminate when they're done. Unless you have like a read line in there at the end there to hold on to things. So it's often easier to open in a command shell if you're not using the IDE to run it. It didn't quite work for me. Uh, yeah, I dragged the file on there and it didn't redirect. I could have swore it did that. But it's clearly not doing that for me here, so maybe that's a .NET thing. Because we do that at work with our .NET applications, we just drag a file onto it. Maybe it's actually something in our code that's doing that specifically on it. And I just didn't, never ever noticed that. You made it run from a file. It's just make it a little bit harder for me to test it, but we'll work around things. All right, if you are online, right, you can create, right, you can create a file, right, people dot text, right, and we could paste into here. So if you actually were, if you do have a file dependency, right, I can go to your file and I say, oh, whatever, I'll change the path to be a relative path so we can actually find it. Students do have a tendency to say, oh, it's that C drive, CS36 or 41, whatever, follow whatever path, a path that exists on your machine, but perhaps no other machine in the world. Files are a complication I try to avoid as long as we can. Program 4 doesn't have it anymore. I think I got rid of it. We used to have that one explicitly file-based, but turns out a lot of people don't know how to work with files in C++, so that was becoming an unnecessary hurdle because file IO is definitely not really a data structures or algorithm thing. Uh, yeah, if you have a menu, that will complicate my testing a little bit. Yeah, perfectly fine. Use debug to start. It's doing the same thing. Basically just calling it's creating a shell, it's calling your exe, and then it just hold on to the shell there for you by adding that press any key to continue bit. Okay, all right. Okay, so back to our trees. How are we doing with our tree terminology? Right, root, leaf, internal node, all that good stuff. All right, it's a directed acyclic graph, which is the next section we'll be getting into next week. Let's see. Any questions about any tree-based stuff just yet? All right, let's build some more AVL trees. If there are any questions at the moment, because AVL trees are slightly involved. No, trees are not next week's test. We'll build a couple more trees and we'll talk about next week's test again. Oh, I almost forgot to talk about expression trees. We do have that to talk about. We'll talk about that next week. We'll do our tree height as we grow this one here as well. All right, so we have no tree. At tree's height, -1. We will add a node to our tree. We now have a tree height of 0. right? The height of a tree is the length of the longest path from root to lowest leaf. And when you are the leaf, you didn't have anywhere to go once you got to the node. So we were 0 hops away. As our tree grows, we now have a tree height 1. And so we'll add height is 0 at the moment here. 1 node tree, we've got our height. Let's put that metadata above. Height of this tree is 1. That tree is 0. Right, so looking at this tree, right, the 45 left subtree has a height -1, the empty tree, and a height of 0 for the right subtree. And the height of a tree is the max of the heights of its subtrees plus 1 for itself. So I have -1 on the left, 0 on the right. Height of the whole tree, 1, because 0 plus 1 there. Okay, what value do we want to add to this tree? It's less than 45. We will not require any rotations. 50, all right, so 50 will cause a double rotation. Again, we start the root. It is a binary, AVLs are binary search trees. Start the root, 50. Now we want to add is greater than 45, so we'll go right. This subtree exists, so we'll have to keep looking. 50 is less than 78, so we'll go left. Left subtree does not exist, so we can go ahead and bring it in. We went right, left. Okay, going back up. 2-node tree is happy. Our 3-node tree is not happy. And our 3-node tree cannot have a height of 2. So we're going to require rotations. 50 will rotate up towards 78, giving us a 45, 50, 78. Nice straight line. And then 50 will rotate again. So I will have 50 up at top. 45 pushed down to its left. And 78. Let's try that again. It's always fun when I'm moving faster than the computer. Right, 78. Right, was dangling under 50, but when 50 moved back up, it pulled 78 up with it. And our height is 1. Right, so our height went to 2 temporarily until we did our rotations to get our tree balanced. Well, you'll see these on the test. So they'll say, build an AVL tree with these values, or add this value to this AVL tree and show me the resulting tree, or tell me which node is going to be alpha, which node is going to say we need to restructure via rotations. All right, what's our next value? $77. And will 77 cause this tree to go out of balance? Yeah, this 3-node tree had a length of 1, 2 hops right from root. We go 1, 2 away. So this tree height was a 2 at this point in time. And then we rebalance because the height of the right subtree was 1 from 45's perspective, and its left subtree was -1, and the distance between those 2 points on the number line is 2, and that's causing it to report being out of height balance. All right, so 77 is not going to cause us to go out of balance. Is there any value we can add to our 3-node tree down here that will cause it to go out of balance? I see people giving me values, but would any of those values cause our tree to go out of balance? Right, we can add a leaf node down under any of our existing leaves, and there's going to be no other possible way to rotate things that would change the state of things. We're going to have one leaf on the lowest level, and there will be one leaf on the level above us. Right? All balancings would consider that to be good. So 77 was the first value that was mentioned, so we can add that. Our tree will get taller because we added another level into the tree, but we do not have any imbalance at this point. All right, so at this point, anything less than 50 will not disrupt our balance. Anything greater than 78 will not disrupt our balance. So anything that goes under 77 will disrupt our balance, right? Because 78 node will get unhappy because it's going to be like one of these situations here or in a straight line. Both leaves, well, all leaves are ultimately connected to the root. The question is, do they have any ancestry between themselves and the root or not? Right? 77 has ancestry between itself and the root, but 45 does not. All right, so early question, we can have a 3-node tree with a height of 2. We cannot have an AVL tree with 3 nodes that has a height of 2. Because any possible way we do that, it's out of height balance. All right, what's our next value that we'd like to add to this tree? We want to throw it out of balance now, or do we want to fatten it up a little? $79. All right, 79. Right, no new level is added. So our height will stay the same. All right. Get our tree in here. Nope, lost the line. Check back later, see if it was missing the earlier one. Right, so anything less than 50 right now, not going to change the height of the overall tree or cause any imbalance. It's going to have to be someone greater than 50. It will cause imbalance, and it will cause imbalance at the 50 node. All right, anything that's greater than 78, since the imbalance will be alpha, this will be beta. So anything that goes in the 79 subtree cause a single rotation. Anything that goes into the 77 subtree will cause a double rotation. What value do we want to add at this point? Do we want to do a single rotation? 78.5. Or we can just make it 81 and this number got bigger. Now it's 97 decimal points. That takes up way too much space. All right, so this is our newly added node. Work our way back up. 2-node tree. Let's be as balanced as we can make it. Go up to here. 4-node tree. All right, that's as balanced as we're going to be able to make it. All right, 3 nodes taking up 2 levels completely. There's going to be a leaf node somewhere. So we'll go up. This level and check. 50 sees a height of 0 on the left-hand side. And our tree has a height of 3, and it sees a height of 2 on the right-hand side. All right, so we're going to have imbalance. All right, because we went into this subtree, we only need a beta node. Beta will move towards alpha. All right, so just grab these down. And move everyone else up. All right, so we have a little problem here. 77. Trying to get carried along with 78, but 78 wants to forget about it. So we're going to set 77 aside in a temporary pointer. So that 78 can grab a hold of its former parent. And then its former parent can go ahead and re-grab onto 77. And that was the code we saw in Geeks for Geeks. Right? Just grabbing onto a few pointers, grab onto the child, and then we'll just relink later. When you're looking at data structures code, I strongly recommend you doing it in tandem, pencil and paper, drawing out the structure as it builds, like we're doing here. That way, when you see pointers grabbing onto things, you can basically visualize that with the paper next to you. So otherwise, trying to visualize things, even with the debugger, trying to help you out there a little bit, that gets very, very dicey very, very quickly. All right. Now, height of our tree. Uh, height of our tree here. Down, get my white space back. Whole tree ends up getting shorter. And we reduce the number of levels. Remember, the number of levels in the tree and the height of the tree are going to be proportional metrics. On that note, there's also a term called depth. Remember, we talked about it, I guess, a couple weeks ago. All right, depth is a characteristic of a node. Height is a characteristic of a tree. Depth is a characteristic of a node. So we have 50 and 97 both at the same depth, right? There's so many hops away from the root. All the nodes at a given level in a tree would have the same depth. Okay, right, so 78 sees a height of 1 on the left, height of 1 on the right. So at this point, there isn't a value that we could add to this tree. No, that's not true. We could add a value over here to make 97 mad. There's no value that we could add to this tree that would cause 78 to become the alpha node. Only node that could become alpha at this point in time would be 97. Are there any additional values we want to build onto this tree, or are we okay for now? Okay, looks like we're good for the moment. All right, test 2. Next week, it's not trees. Now, let's go there from the student view. What week is this? 4 weeks, 5, 6 weeks, 7-ish, somewhere around there. Yeah, week 7. Okay. All right, moving along. Halfway point is getting close. That is not the practice test. Let's try the practice test, shall we? Yeah, it's funny. I just had it right there. Practice test. Yeah, before you know it, we'll be reviewing for the final. Okay, reverse Polish. Remember all that fun stuff? All right, that was the 4, 5 plus. All right, 9 becomes 9 sort of thing because we're building our stack. 24, right, plus, minus, multiply. All right, this will be 3 plus 4 first, gives us 7. 2 minus 7, -5. -5 times 1 gives us -5 at the end final state. Bubble sort. Remember bubble sort. Bubble sort is comparing adjacent elements. All right, it's gonna do potentially a lot of swapping here, but because it's just taking two values side by side and saying, all right, looking at how tall they are they in the right order, right? Put the hand over, let's see whose head's taller than the other, and if they're out of order, they swap them in place, right? Be very easy to do a live demo with people for a bubble sort. And have everyone just stand in a line, and you go to the first two people and look at them. All right, do we have the taller person in the appropriate spot? If not, tell the two people to swap places, and then we'll slide down one, look at the next two people, which might have the same person as we just looked at, or might not. And if they're not in the right position, they swap. All right, and we'll go down the line, and we'll have the tallest person at the end when we're done, and we'll reset back to the beginning, repeat and repeat. I'm sure there's got to be a YouTube for that, right? YouTube has everything. Live person bubble sort. Surely we can find one of those, right? YouTube. Probably means they're just going online. Using a computer. That's a terrible way to teach. We can have people lining up. Oh, wait. This might just be a person talking. Oh, well. Good exercise. Try to find a person. Okay. Interesting hit for a bubble sort search. All right. Okay, back to our test. Where's our test? There we are. All right, selection sort. And this is where you hunt down the shortest person, grab them, front of the line. Then you got the next shortest person, grab them, back of the line of the sorted line, sort of thing, and rinse and repeat. 100 full days. If anyone wants to find me those links, I'll add them to Canvas because it's always good to have association, right? Association is a good way to remember things. But right, the word select, right? In the selection sort, we're selecting. That's the core operation is to select the extreme value. All right. Let's copy that link. I'll drop it over here in the side, and then we'll Oh yeah, I have seen that before. But yeah. What are the odds that these are data structure students? All right, merge sort. Our n log n sort. Our actual one and only n log n sort. Right. All of our other sorts are O notations n squared. O notation, unless qualified, always worst case. All right, so I asked, what's the O notation of bubble sort? N squared. I asked, what's the best case O notation for bubble sort? That's the one we can then say linear. That's where other answers come into play. Merge sort is the only n log n sort we have on test two, right? Recursion, base case, production rule, that fun stuff, multidimensional arrays. And okay, so do we have any questions about any of the answers on the practice test as soon as it loads up? And this is why we have 65 minutes instead of 60 minutes. This was our paper test would have 60 minutes because, technology is less of a problem, right? Do the reverse bullish, type your numbers, math. Feels like we went over this already, but that was more than yesterday, so we've already forgotten everything. All right, you can see some code on the test. Tell me what it is. Question 9. Code. What's your question about question 9? All right, implement add to tail. All right, so we have a tail node. Add to tail. What are we adding here? An int number. Oh, terrible paragraphs. That makes just too much white space. All right, if tail's null or zero or null or whatever you want to call it, null pointer, who cares? One of those. And the list doesn't exist. So we say head equals tail equals new link. Right, I don't actually have the constructor there, so I need to add constructor for my node class. ctor for link, making this line valid. Otherwise, the list does exist. And since it does exist, we can add things along here. All right, so we have slightly redundant code because I have new link twice. Right? Better just create the link in the first place. We're adding a link. So we do that once and then just set the links as appropriate. Right, this is double linked list nodes. We have an extra pointer to take care of. We have L previous equals existing tail. We have tail next equals this one. And then we have tail is equal to this node. Yep, double linked. It's got the previous and the next pointer. So it's just standard doubly linked list node, right? And the list has a corresponding head and tail, which should be required for a proper doubly linked list node. Go over the big O for the sorts. Sure, big O. for all the sorts. Quick sort and squared. Merge sort and log in. Bubble insertion selection and squared. This big O notation is always worst case. Yeah, the link's in the module section on Canvas near the big O. Boom. Let's get this out of the way here. Modules. Let's minimize the lecture code and minimize the labs. I don't know why that has to show up over there. Big O notation, big O cheat sheet. Yeah. Omega and theta are the other two asymptotic complexity notations. Those omega notation. Right, they're just going to show you big O notation's an approximation, right? Whereas trying to remember because it's big O is an upper bound. It's not going to go above big O. And I'm trying to remember if it's theta or omega. One of them is the lower bound, and then one is this is the actual, basically the functional notation type thing. But that's where the math gets a lot heavier. But it's basically the same concept. It's just tends to be a little more precise. But if you want to read big O versus omega and theta notations, those are three different ways for our asymptotic notation. Right, and then you see lovely graphs where we have the functional notation. That's the actual cost for the algorithm to do its thing for a given size n type thing. Yeah, we had the test at the start of class last time, right? I presume we want to do the same thing again next time. Unless there's a large movement. Is there a rally? We're gonna sign a petition to have it in the middle or later? Yep, so we'll have tests to start off the class, and then we'll get on lecture. We have just based on it tree I mentioned earlier, the math tree. Oh, wow, brain fart. Mm-hmm. Anyways, we'll talk about that tree later. Next time, double check we're doing good on 2-3 trees and AVL trees. Sure, any additional tree questions, and then we'll get into we'll start graphs. All right. We'll take 5 minutes and then we'll go into lab time. We'll talk about the last labs that were due. Any other code questions, but there's no more lecture material for tonight. So if you're not hanging around, I'll talk to you later. Otherwise, I'll talk to the rest of you all in 5 minutes.